Hi again. The last movie we talked about control volume analysis, and we mentioned that we can apply it to different physical laws. Let's see two examples and let's see how we can apply it to a real problem. For example, we know conservation of mass from physical laws that the mass of the system will not change. Mass cannot be generated and cannot be destroyed. So if you take a system and follow the system, the mass of that system should remain constant. In other words, dm of the system over dt should be 0. In a Lagrangian description, that would be 0 being equal to d over dt of this term. And if you use something like form A, for example, of Reynolds transport theorem, for a control volume, and in the language of a control volume, it means that the net rate of change in the mass of a control volume should balance with the flux of mass and fluid elements coming in and out of that control volume. So you can clearly see that for example, mass, this becomes a relatively simple equation. If the system is a steady state, this term will be 0, and this will tell you that the flux of things coming in and the flux of things coming out in a control volume should balance each other. I always like to say that it's very much like, for example, if I eat a lot, but I don't do anything in terms of activities, that accumulated amount of calories is going to lead to me gaining weight. But if I go and do activities more than what I gain, I'm going to lose weight. That's exactly the same kind of analogy in terms of knowing what's going to happen to your system in terms of accumulated property if you are not having a balance between inlet and outlet. If the inlet is giving you more than what you're exiting in the outlet, you will accumulate that in your system, or in your control volume in this case. The same concept can be applied not only to a scalar, but to something like a vector, like velocity. Or in other words, for the idea of linear momentum. Conservation of linear momentum from physical laws tells us that the summation of forces acting on a system should be equal to the net rate of change of the linear momentum of that system. The net rate of the net linear momentum of a system is this integral, rho times the velocity vector integrated over the entire volume of the material volume. So the rate of change of that, which is equal to the sum of all the external forces, surface, line, and body forces, everything from external world that exerts a force on our control volume, is equal to, again using form A, the rate of change of momentum accumulated inside the control volume plus the flux of momentum coming in and out of our system through the control surface. Now, we have seen that this is useful in many different examples so far in Module 1. But let's try that on an example that actually should ring a bell to you guys. If you look at the picture that we have chosen for Module 1, it's a picture of a helicopter. And let's think about what we can do using these concepts in terms of analysis of a flow around the blade of a helicopter. This can be actually a very challenging problem. A rotating blade with all the vortices and things involved around it cannot be really easily tackled unless we use some simplified approach like control volume analysis. What I have done here, I have plotted the geometry of the simplified geometry of a model for a rotating blade. My rotating blade, which has a cross-sectional area A, is shown here. It's rotating like this. So I can imagine that there are some fluid elements very far away from this rotating blade that will not feel the motion of the blade that much. They have probably 0 velocity. Pressure there is probably P ambient. I call that a station 1. But gradually these fluid elements get sucked inside my rotating blade. As I'm giving them momentum and as I'm giving them velocity, knowing the concept that we just talked about, conservation of mass and streamlines, representing whether I have acceleration or deceleration, I should have probably some converging streamlines. Streamlines converge. They pass the blade with a velocity that I can name as u1. And as they pass this rotating disc or rotating blade, they continue their converging until some point further down the blade where they reach almost a constant velocity u2. And after that, they probably don't accelerate. If they are not accelerating anymore and they remain as a constant velocity u2, I can clearly see that the shape of the streamline after that should become almost flat with no change in cross-sectional area. This is a very simple way to just visualize the flow around this object. Now, if we are interested in terms of how much thrust, for example, this blade is getting from this kind of kinematics of flow around it. And this truss probably should be enough to balance the weight of a helicopter. We need to somehow connect that truss with velocities, densities, and other given properties that we may like to take from this model. One way to think about it is the following idea, that probably to think about conservation of linear momentum will be a useful idea. I can take a big contour volume, and let's take that together. I can take a contour volume that can go actually all around this closed streamline. So this dashed area is the surface of my contour volume, and I close it here down there. And I can write down, for example, conservation of linear momentum for this contour volume. So if I do that, what I get would be conservation of linear momentum for the CV that I've chosen. So the force that I described as thrust, negative of that, easy, is exerted from the blade to the fluid elements. That means that that goes to the left-hand side, the summation of forces acting on my contour volume. That's the force that is exerted on my fluid elements in the contour volume that I've chosen. So this contour volume basically is everything other than the blade. So everything inside this other than the solid geometry of the blade that I've taken out of my contour volume. And on the right-hand side, I will have d over dt of rho v dv integrated over the entire contour volume, plus integral of rho v minus vc dotted to n dA. The problem is a steady state, so this term goes to 0. And now I can calculate fluxes and connect that to the truss. I'm not going to do all the algebra. This is the part that in previous videos we have shown helps really to form a table and tabulate all the entries and use them accordingly. I'm going to just show you the final answer. And trust me, it's just one line of algebra that you can do. The thrust force becomes equal to rho u2 squared multiplied to the area at position 2. And if I take a look at this area at position 2, it looks that area at position 2, A2, is smaller than the area of the blade. It's smaller by a factor c, where c is between 0 and y. So let's call A2 being equal to CA. So C is unknown, and we want to calculate it. So this gives me that the thrust force is rho u2 squared times CA. And I can call this equation 1, and see what else I can derive based on my knowledge of module 1 so far.